Well, welcome everyone to Coping with Non-SOLIDWORKS Users Data. I'm Brandon Nelms. I'm a Senior Application Engineer and Team Lead based out of our Indianapolis office. So let's take a look here at a common supply chain workflow. We've got a bunch of vendors and they're all using SOLIDWORKS. So we can create an assembly and design our part right in context to theirs. And of course, as a result, it's going to fit perfectly, right? Now, I know everybody watching this never had this happen, but let's go ahead and humor me here for a second. But let's say the phone rings and it's the vendors saying, hey, there's been a part change and you shall like it. But since they're using SOLIDWORKS, really it's no problem. We just go in and update our assembly and everything rebuilds and it's perfect fit every time, right? And that's the way it works every single time. Okay, right. Obviously, that's not the case because unfortunately, not everyone gets to be awesome like us and use SOLIDWORKS. And unfortunately, they've got a bunch of different systems. So what do? They send us translated files a lot of times that then end up needing to get repaired and cleaned up so that we can get SOLIDWORKS parts out of those that we then can use for our in-context assembly to create our perfect fitting part. Now, out of the gate, this might look a little intimidating, but now that everything's done, it shouldn't be too bad, right? Surely the vendors wouldn't then just, decide to make changes to their parts that would require them to then translate those files again, which would mean that we then have to repair those files again, only to find out that, those parts cause errors in our design. And then we got to go back to work and do a bunch of repair work or redo work from before to get our perfectly fitting part. So I'm sure nobody has had that issue. We may have had people that have ditched in-context design as well as a result of this. I know a lot of customers that have said because of that crazy process, they're not even going to use in-context design. So instead, what if we had our parts and we got a part from a vendor and we just use those directly inside, those native parts directly inside our assembly and get our design relative to that. Where there's no translation, no repairs, just an in-context part that references other CAD data. And then, when a change were to come about, our vendors just would send us updated versions of their CAD files in their native CAD software. And then we could update our assembly, get a new version of our file, and everything works smooth. Well, at a high level, that's how 3D Interconnect works. No translations or repairs, just a referencing system. But we're going to get into 3D Interconnect a little bit later. So when I look at dealing with other CAD data, there's really three different areas of focus. Importing data, that's actually opening files in SOLIDWORKS. Dumb solids, which really gets a bad rap. And finally, this relatively new technology called 3D Interconnect. So getting started with importing data, there's a bunch of different options. Then we have to talk about how we must deal with this thing called import diagnostics. And last, if all else fails, what kind of repair techniques can we use to get clean geometry? All right, so let's start with obviously my favorite, and I'm sure everyone's as well, translation options. Maybe my sarcasm wasn't clear enough there, but obviously starting in 2017, import and export system options were actually introduced. And these weren't options that were new. They were just only visible previous to that through using the SOLIDWORKS file open window. Now they're in the system options. And by far, the favorite question I always get asked is, well, what options do I use? And if you go through all of the different combinations of options that are there, it's a lot. In fact, the last time a colleague and I went through this, we tried to figure out what is the total number. We calculated 1,486 unique combinations of options for importing purposes. And similarly, there are a bunch of different export options as well. Now, out of the gate, you might think, well, that's a lot. That's too many. It just means we have different options, which we're going to use a little bit later as potential techniques to deal with issues that may arise from data that gets imported in a faulty manner. Now the question is, what kind of files can we open in SOLIDWORKS? Native files are usually your first best bet. If you start with a native file format, you're going to eliminate one of the file translation steps. If you recall from the earlier graphic, a lot of the processes will send me a step every time. Well, if we can eliminate one of those translations, a lot of times we can get cleaner data. Not every time, but a lot of times. So remember that we don't have, not only do we have to translate the neutral format into SOLIDWORKS, but that other CAD system has to translate out of their format into that neutral format. And essentially by using the native, we're eliminating that step. Now for the neutral formats, in order of preference, most folks say, what's the very first one? What's the neutral format we want to use first? And first and foremost, it's the Parasolid. That's actually the modeling kernel, which is used by SOLIDWORKS. It's the under-the-hood math engine that SOLIDWORKS uses. Then the second is the step file. So it's the standard for exchange of product data, and it's actively maintained right now. The third is actually the ACES file. The ACES file is actively maintained right now by Dassault. And then the very last, and if I could put it nearly off the bottom of the screen, I would, is the IGES format. This IGES format is actually fairly old. In fact, if everyone can recall back to when the Olympics were in Atlanta, yes, the Olympics were actually in Atlanta. When the Olympics were in Atlanta was in 1996, and that's the last time the IGES standard was updated. In fact, the group that was involved with the IGES standard said, we just can't do this any further. There's limitations. And so they decided, hey, we're going to create this thing called the step file. And so basically that group just abandoned what they were doing in the IGES format and started the step and have moved forward with the step. So it actually shocks me that even IGES works at all as well as it does. But we want to steer clear of IGES files if we can. Now, some of you may have looked at that list and thought, well, what about like DXFs and DWGs? We absolutely can use those for part creation. So let's take a look at that process real quick. When we look to open a DWG file format, we're immediately presented with two options. One is to create a drawing, and the second is to create a part using that DWG data as sketch data. Unfortunately, DWG and DXF data isn't parametric. It's really just a very, very straight lines. So in the import process, there's an option for SOLIDWORKS to infer geometric constraints from that line data. And we're presented with controls like what layers we want to bring in, units, or even merging points together. SOLIDWORKS translates that 2D data into usable sketch entities. And now that we have 2D sketch data, we can use SOLIDWORKS's 2D to 3D conversion tools. There are tools such as Align Sketch, which allows us to move all the sketch entities simultaneously, redefining their position. And since these entities were underdefined, simply dragging them would risk changing the overall shape. We can select specific sketch entities and assign them to view orientations, like maybe the front view in this case. We'll say this is a front view sketch. And we can then simply box select our right view sketch entities and assign them as a right view sketch. Now that we've moved sketch entities to the specific view orientations, we can hide our originally imported sketch and at this point, we can clean up any sketch entities we want to remove and also fully define our sketch planes with the Edit Sketch Plane tool. So even though our sketches were moved to the specific view orientation we wanted, we still have to define what plane they live on, just like any other sketch, because this same process could be used for us bringing features that may not live on a primary plane. With our sketches in place and planes defined, we need to clean up our right sketch so it looks like the profile we want for our revolve feature. And now I'll align my sketch, and I need to start adding in some dimensions to control our downstream design intent. What I usually do is add any specific dimensions I want with the Smart Dimensioning tool. And to then really speed up the process, I'll use the Fully Defined Sketch tool. I could tell SOLIDWORKS to turn any positional relations into geometric ones and define a dimensioning coordinate scheme to get a clean, fully defined sketch. Now I simply use the sketch for the feature I want, like this revolve. At this point, I follow the same process as before, and I'll add in the dimensions as necessary. Maybe even convert sketch entities to the new sketch, create new features from the sketch data until I get my final parametric 3D model that I'm after. So keep in mind with translation, there really is no one-size-fits-all solution. And we want to try and use native first and then parasolid and then step files. All right, so now let's talk about my real favorite part actually, which is import diagnostics. So right now, you might have opened up a native CAD geometry like this, maybe that you thought was supposed to be a solid model, only to then see it with a bunch of surfaces. So let's talk about why that's the case. To really understand why we might have translation problems, let's look at the process. So we start with a user creating some part. That part is actually created by talking to a CAD system to come up with some instructions that then go to the kernel. The kernel is what makes it happen. It actually calculates the shape. And we now have what we call a CAD file. It's actually comprised of 3 different elements: a header, or kind of like the file properties, instructions, which are kind of like a binary feature tree, if you will, and a database, or a finished shape. Now, if we want to go to another CAD system, that CAD system has to read the file and create instructions to then give to its kernel to then create a part, which is real simple, right? So why do we have problems? Well, first of all, different CAD systems have different tolerancing limits, and so a gap may be seen by one system compared to the next. Second, not every CAD system speaks the same language or even uses the same nomenclature, so instructions could be missing or not translated. Also, on that same concept, not all CAD systems instruction sets are available. A lot of them are proprietary. Altogether, it's why we don't get a feature tree during the translation process. And last, not all geometry itself translates across systems, so a surface for a feature may not really be understood between 2 different systems. So if you look at the file open process within SOLIDWORKS, you'll see there's a ton of different files that we can open. And when we're opening this dreaded IGES file, see we get a dumb solid, or the database part of this CAD file. But to move forward, we absolutely have to run import diagnostics. Don't necessarily have to do anything about it, but we have to run import diagnostics. When running import diagnostics, we see we've got a faulty face and potential gaps in the geometry. With a right click, we can even reorient the model to see the problem face. And if we select wrong, we're told there's a general geometry problem. So real helpful. It's awesome, right? We can select the specific face, any specific faces, and try and repair them, delete them, or recheck them to be sure if there's really a problem. But a lot of times we start with the attempt to heal all, which tries to repair the faulty faces and gaps all together. And now you can see we've got clean geometry to work from. So I did get a question in the chat real quick of what is the best curve setting for importing files. And just real quick, the best, quote unquote best, it all depends. Usually that's something that I will adjust. It all depends actually on the import diagnostics. So using the import diagnostics as a tool to make sure we get good clean geometry that comes in. And you can use the curve settings or the different import methods to try and minimize the amount of work you have to do with getting clean geometry. All right, so at this point, what is import diagnostics actually doing? Well, first, it's identifying areas of the geometry that are faulty and will cause downstream problems. So it's identifying those problem areas. Second, it provides a set of automated tools that can fix the problem. And most importantly, it tells us that we've got good, clean geometry moving forward. By the way, another tool we can use to check even just straight up SolidWorks geometry to make sure everything is okay is the check command. So you can activate it by going to Tools, Evaluate, Check. So why is import diagnostics important? It drives to a clean solid, and we can get fewer downstream problems. So if having clean geometry is so important, what's our last resort? Well, it's repairing it. Sometimes import diagnostics can't get clean geometry, so what do? Try it again. So sometimes if it's not working, we can always run import diagnostics again. Another trick is to what we call round trip the model, which is basically save it out as a parasolid and then try re-importing that parasolid file in. And a lot of time, or sometimes we will get those two steps will help to close any of the gaps that are necessary. We can also try different import types. Remember all those different options that we talked about? And this is probably one of the areas that I think is least used across the industry as I talk to different folks. When asking for files from customers, if you think about how easy it is for you to save files out for others of simply file save as and then send, it's not really that challenging or a lot of work for our vendors or our customers that we might be interacting with on their systems either. So simply asking them when they're going to send a data set over, send me 2 or 3 different options. Send me a parasolid, send me a step, send me a native. It sounds like a lot of work or I'm asking for a lot, but it's really just a couple of different options. It's simply file, save as, and any one of those might be the easiest one to use. So asking for a group of files is oftentimes the best starting point that most people could do right away to get a lot better results. But at the end of the day, if we can't get to anything at the very end where we have to get clean geometry, we can always recreate problem surface areas. So if we've got a persistent import diagnostics problem, we can always recreate it with surfacing tools. So let's take a look at a part that has some problems we can fix with the import diagnostics tool. So we've got a faulty surface here. If we run import diagnostics, when we run it, there's really no combination of healing all gaps, healing all faces, heal all. That's really going to get us to good clean geometry. In fact, even after multiple attempts, there's still going to be a faulty face left over. So we've got one faulty face that remains. So there was a question to the group about importing sheet metal files where other systems can work with coincident faces. And that is true. That is something I've seen as issues as well. Don't have a specific workflow for that specific instance right off hand, but I have seen that as well as far as getting it into a usable sheet metal part. And then there was also a question about preferring parasolids over native geometry. And usually it depends on workflow. And if you stick around, we're going to talk about 3D Interconnect and how that works. And so that can be maybe what is going to lead to answer your question of whether or not to use a native file or a parasolid. So let's take a look still at this example where we've got faulty geometry. And we can see the problem here is where this blend comes together, where these three fillets all meet together. So to rebuild the fillet, we're going to need to rebuild that original corner. And to do that, I'll make copies of what I like to call the hard geometry. And these are any of the faces that we know we're going to keep during this rebuild process. So simply setting the offset to 0 is a copy surface. And then now we need to remove any of the faces that we're going to replace or rebuild on our bad model. And we can do that with the delete face command, simply selecting the faces and choosing the command from the right mouse button menu. And now we need to recreate that hard edge corner. So to do that, we'll need to extend edges of our original surfaces so they all intersect. And we're going to do that using the extend surface command. I only extend the edges that relate to the corner I'm trying to fix so that it'll knit together easily later. And you'll notice that since these are individual bodies, we have to repeat the command a couple of times. And a real quick shortcut is just to continually hit enter after done with a command. And then you can repeat the command at one time after the next. Now it's time to combine these. With the trim surfaces command, I can use the mutual trim option, which allows me to pick only the faces I want, removing the rest and knitting my selection together into one surface body. So for the mutual trim to work, all of it has to be able to be knitted together as one body. So now with my hard corner surface body, I can add the multi-radius fillets I want into my corner. And prior to starting this, I checked what the radius values were using the minimum radius of curvature function, which is also available within the check command. So that's how I know what values to put in. And we can put those right in on the surface body as well. Now that I've got a good corner for the blend for the fillet, I can knit my surfaces together, and while knitting them together, also use the create solid option to get a good final solid body that can be used for maybe some downstream processes, maybe a mold that I'm creating from this. So here's a summary of the process that we just followed, along with a couple of other techniques like spline on surface and then filled and lofted at boundary surfaces as well, including the check entity as well. The question is, why bother with all of those different steps? Well, we now have a model that can be used for downstream edits, like maybe moving or removing a hole. Ironically enough, it actually leads to smaller file sizes. Even though there's additional features, bad geometry often causes a lot larger file sizes. And performance. Oftentimes I see poor performance in drawings or assemblies stem from bad geometry. And miraculously, when we go clean up the geometry, all of a sudden those crazy problems of I can't do this or why is this drawing acting crazy go away. So there's a question about, other than using for mold making, is there a reason to make it solid? In fact, that's a perfect question. I appreciate that because uh, in doing import diagnostics, when you run into problems, you definitely have to decide whether or not the effort is worth it, right? Is the juice worth the squeeze? If it's causing problems downstream, then yeah, you need to, that's the starting point for me. It's the foundation to the house. And if the foundation's faulty, I don't know. There could be an issue that's caused up in the master bathroom because the whole house is sinking because of the foundation. So other than, if we're not having problems with it or we're not referencing the faulty geometry in our assembly, we may just use that as a surface body, or eliminate portions of it that, delete that bad corner out and just use a surface body as a reference because I'm just trying to use it as a picture or something. So it's actually a great question. And then how does that affect file size? You'd have to test it. So then there was also a question about cannot risk changing customers' model and product. Options there is obviously to review any of these kinds of scenarios. I would say you still need to review with that customer whether you make the change or not, and understand the concern. But that is something that if you're still experiencing problems, or we're still trying to get to these issues being taken care of, these benefits, it is something that is going to be resolved. Otherwise, you might have to do crazy workarounds to get that taken care of. Now, what about more complicated scenarios, right? More complicated or missing geometry. A lot of times, once we've removed the bad geometry, you can still use the good geometry, right? So you could still just use this as a surface body, and it references everything that you need. Or you can use traditional surfacing techniques to rebuild areas that you need. Or leverage symmetry, right? So a lot of times what might happen is that because of the way that the translations happen, if you go through and delete out bad geometry and have that phone conversation with the customer of what are you expecting, what are you needing, and then you say, hey, is it symmetric across the center? Yeah, it is. Okay, well, no problem. I can cut this and then mirror it across. Sometimes a quick phone call or a quick email of getting a basic understanding of what it is that they need, and asking those questions can save a ton of work. All right, so when importing or when repairing imported geometry, make sure to leverage surfacing techniques, and you'll see increased performance downstream. So remember, when it comes to importing, there's really no one-size-fits-all solution. It's really critical to drive to a clean solid, and even that if that means leveraging the surfacing techniques. So now let's talk about dumb solids. Personally, I really hate this term, dumb solid. It's what the industry term is. It's got a really negative connotation, in my opinion. Really, what we're talking about is the database portion of the CAD file, or the end geometric shape. And even though there isn't a feature tree, you can still really manipulate the geometry with tools like delete face or move face. You can add additional features. You can even pull out geometry from the end shape and add them as features that we want for our tree. So let's take a look at manipulation with delete and move face. Let's say I have this dumb solid where I wanted to remove the mounting slots. I simply select the faces I want to remove, which is a process I can speed up by holding the Control key and select tangency from the right mouse button menu, and activate the delete face command through a right mouse button menu as well. The delete face command is super powerful. I can remove faces for further surface modeling, manipulation by using the delete option, or remove faces like they never existed with the delete and patch option, or remove faces and fill in the resulting gap with a new contact or tangent filled surface. So in this scenario, I'll use the delete and patch option, which will remove the faces, and SOLIDWORKS will extend any open surfaces to create an enclosed volume. Now for my application, this part's too tall, but if I use a cut, I'll lose the chamfers. So instead, I can use the move face command, which can also be accessed through a right mouse button menu. And in my opinion, the move face command is amazing. With the move face command, I can offset, translate, or rotate one or multiple faces at one time. There's even a handy selection toolbar that allows me to pick multiple faces at once. And now I can move all the necessary faces together by either dragging the triad right here in the graphics, snapping to a specific dimension from the on-screen ruler. You see that snapping to it if I'm close to that ruler, or specifying my desired distance from the property manager. So how far do I want to move this? So let's move it down by 1/4 of an inch. So even though we have a dumb solid, we don't start from scratch. And the delete face and move face commands are some of the most powerful manipulation assets we have at our hands. Now, the next way we can work with dumb solids is by adding features. So we got rid of the slots on the feet, but I want to add some counterbore holes with the hole wizard. Now, this dumb geometry is perfectly fine for use for sketch faces or adding sketch relations to get my holes in place. We can take our design intent further by adding patterns. In this case, I'll mirror the holes across the front and right planes just as I would if I was designing any other SOLIDWORKS part. And if we need to add a fillet, sharp edges here, fillet, no problem. We can select any edge and even use our selection toolbars like we would normally on any other part, just like we created it in SOLIDWORKS. And even though we started with a dumb solid, we're keeping track of changes we've made and creating our own parametric feature tree that can be modified just like any other part. This is probably one of my favorites, is what did I start with and what manipulations have I made? So getting an import from a customer, I now can use my rollback bar to find out where did I start and where did I go. If I have a design tree, I can't keep track of changes that I've made. If I change this dimension to that, I added a new feature as easily as I can here. I know exactly where I started and exactly what I have done from start to end. So what do we want to do? What do we do if we need to add features to an imported part? We don't start from scratch. And know that we can use all our SOLIDWORKS features just as if we started the part in SOLIDWORKS. Now, there are times where we do want a full design tree, like a classic sheet metal part, so we can get a flat pattern. And since the instruction set portion of another CAD file is proprietary and we really don't get that tree, we need to create it, or we can using FeatureWorks to recreate a feature tree from a set of logic rules, and that's what FeatureWorks is. So if we right-click on a dumb solid, we can access the FeatureWorks option, including whether or not we want to overwrite our existing file or create a new one. We can choose to enable dimensions and choose what scheme to use, or even infer sketch relations like horizontal and vertical. If we want to get really in depth, we can even control the order of feature recognition that the FeatureWorks uses. If we want to go crazy, we can even control whether or not FeatureWorks combines specific features. But for this, let's just use the default settings. So FeatureWorks can be activated a couple of ways. One of which is FeatureWorks can be activated a couple of ways, one of which is by right-clicking on the dumb solid, going to FeatureWorks, and selecting Recognize Features. And this launches an interactive manager that allows us to choose recognition mode, what type of part we're trying to create, and even what specific features do we want to look for or not. Since this is a sheet metal part, we choose what our fixed face is for the flattening process and select Next from the Property Manager. FeatureWorks goes through automatically recognizing sheet metal features and shows us a preview of the design tree in the dialog box. We can see where the features came from, and if we're happy, select OK. FeatureWorks creates the part, and since this is a sheet metal part, tools like Flatten work perfectly. Our part has a full feature tree just like we designed it in SOLIDWORKS. While it's not necessary that the same design tree, not necessarily the same design tree we used that was used from the other CAD system, we do have a parametric features that we can still edit, reorder, suppress, just like any other SOLIDWORKS part. We can also edit the corresponding sketches for these features as well. Another way of activating FeatureWorks happens directly from the user interface. By simply selecting specific features like these holes, a right-click reveals the Edit feature. And FeatureWorks is activated in the background and recognizes these holes as Hole Wizard holes. This is now fully editable, just like it was originally designed in SOLIDWORKS, and I can change the size, position, or type to get the design modification I'm after. So when it comes to FeatureWorks, here it is. I know, shocker, right? Don't start from scratch. Also, we want to be sure to only use it for features that we don't always, we only want to use it for specific features. We don't always have to use it for the whole part. So when it comes to dumb solids, don't start from scratch. Don't start from scratch. Please, please don't start from scratch. I say it enough, hopefully. All right, so now let's talk about this thing called 3D Interconnect. What is it? How do I use it? Plus, we'll talk about some additional benefits. First and foremost, what is it? Now, I know everything in SolidWorks has the most intuitive name, right? Well, not everything does, obviously, but 3D Interconnect, in my opinion, really does. Because if you think about it, what is 3D? That's CAD data, right? And then inter means between, and connect can really be thought of as like a linkage. So it's a link between CAD data. But really, it's a more seamless design process that really just focuses on SolidWorks instead of what the other system is. So at its core, it's a referencing system for other CAD data that has a couple of different workflows that we're going to discuss in a little bit. So how do you enable it? Well, by default, it's actually on, but it's in the import section of the system options. And you should be aware that it is on by default. So 3D Interconnect, what is it? It's an intuitive multi-CAD platform. So if you hear that term, that's what it is. And it's a CAD, at its core is a CAD referencing system. So let's talk about how do we use it. There are a couple of different workflows. First is as an assembly reference. Second is as a derived part. And third is merely as an import option. So let's take a look first at an assembly reference. We're going to add an inventor assembly to our SolidWorks assembly. So I've got a SolidWorks assembly and I want to add a supplier's inventor assembly right into my assembly. And I'll start by going to insert a part, just like I would for any other SolidWorks part, but I need to be sure that I'm filtered for the appropriate file types. So either all files, or in this case, we'll go to an inventor assembly. So let's browse to the inventor assembly that our supplier provided. And we don't actually need inventor in order to open and view these files like we used to in the past. The inventor assembly comes in just as if it were a SolidWorks assembly, and everything I'm used to doing with SolidWorks models applies, like mates, displaying section views, or model transparency. It all works the same. Remember, the inventor data has not necessarily been translated. No new files have technically been created, and there's no geometry conversion issues to deal with. In fact, if we look at the feature manager tree, we'll see these icons, which indicate that it's an externally referenced CAD file. That's what that little arrow is. Mates can be applied just like we'd expect, including mates to the reference geometry. Center up the battery pack in the compartment, and go ahead and mount it flush against the back of the housing. And then slide the rib pack down and mate it on the rib. And notice the retaining bracket is how it's too far out from the battery pack. So we need to build in some design logic to take up that clearance, which requires an in-context relationship, which you wouldn't really do that with dumb solids. Notice how even the holes and the fasteners move. If we were to do that traditionally with a dumb solid, we're just asking for potential problems downstream. Because what happens when there are changes? Because boy, that was fun, but what about when I need more power, right? My supplier sends me an updated version of this battery pack, which is for the more power. What does that update look like? Well, in the Windows folder, we just replaced the old inventor assembly with the new data. Now back in SolidWorks, if we look closely at the feature manager icon, there's an update symbol. The software understands that there's a newer version of the model, and a right click to the update command is really all that's necessary. And watch, The retaining bracket automatically adjusts to fit that. Super easy. So let's take a look at our second workflow. So we call a derived part. It's basically where we're going to make some modifications to a supplier provided part. So we need a gear plate for this drive motor, and our supplier provides this as a Creo file. Notice how PTC uses .1, .2 convention to keep track of different versions. Now let's open the part in SOLIDWORKS. And just like you saw before, there's really no translation necessarily going on here. Let's take a look closer. From the featured tree, it basically is creating a new part that is a reference to the old part, or it's a reference to the Creo part. With the default reference planes, a material folder, but instead of a dumb solid import, we see that it's linked to that Creo file. Now this gear plate comes in multiple sizes, but we don't anticipate needing a change to the base geometry. We do want to do some additional machining. So from the SOLIDWORKS design library, we can drop one of our standard keyway cutouts and a radial slot. It's going to give us the correct rotational range of motion. And now we'll insert the part into the assembly and mate it in position, just like we would with any other SOLIDWORKS part. But once we get it into place, we see that we were supplied with the wrong part. It's not the right size. The diameter is correct, but it's the wrong size pocket. So that machine slot's going to not line up there with our radial slot, and we need to get our supplier, to send us the correct part. We give them a call, and of course they say, "Oh, wait, which one do we send you?" "Oh, the .1." Of course, that's not right. It's the .2. So, how do we deal with modifying a part? Well, it's really no problem. So how do we do that when we get from our new vendor? Well, our supplier sends us the correct one, which is indicated by a .2. Now over in SOLIDWORKS, we see that there's a refresh symbol, which indicates that there's a new version. So we just right click and update. And the replacement part looks great. And notice how the assembly is up to date, fast and error free. So now the native Creo part is fully associative to our model. Now, the last workflow is breaking the link and creating the import, just like any other solid. So let's insert a native solid edge drive motor assembly. Now we can position it in place with smart mates and align the mounting holes just like we would normally. But in doing so, we'll find out that the center hole, there's a problem. It's not really in the correct position. Our supplier doesn't have a different option, and it's going to be cheaper for us to just buy the mass-produced one and then machine that plate ourselves. So we just want to break the link and make our own version in SOLIDWORKS rather than redesign everything. So simply right-click, break link. Incidentally, this workflow is basically how we've actually dealt with imported geometry in the past. After we've broken the link to the assembly, if we open up the assembly, we see the individual parts are still linked. And so we can break those links. And we then break the link for the individual part we want to modify. So we can do that right-click, break link, or on the tree itself, or on the part. So right-click, break link, breaks the link, and now it's back to a dumb solid. Once we've broken the link, SOLIDWORKS performs the import, and we've got a good high-quality geometry. Converts over our dumb solid in its own file, and now we can make our specific design changes with direct editing techniques. So if we use that FeatureWorks of editing, recognizes the hole, and it's fully editable. So if we go back to our assembly, since it's an M7 hole that it recognized, back in our assembly, when we do an in-context edit of the position sketch, we can select other and make it concentric, to our hole, moving it just slightly so that it's going to fit perfectly, which maintains our design intent. So how do we use 3D Interconnect? It's as an updatable reference or merely as one of the different import options for dumb solids. So that was also something that step files are that way now as well. All you have to do if you want back to the original is update as breaklink. So let's close out with some of the other reasons that we might want to look at 3D interconnect technologies. For a simple case study, we got an inventor assembly from GrabCAD. And using our standard import methods in 2017, this file had 759 components. It took 12 minutes and 51 seconds to open. And in order to open it, you had to have Inventor View installed. And there are hours and hours of import diagnostics work that needs to be done, not to mention no link back to the original CAD file. Using 3D Interconnect, same 759 components, only took almost 4 minutes, so 3 times faster. No need for Inventor Viewer. Doesn't require any kind of import diagnostics, depending on what you're trying to do with the file downstream. And it also has links back to that native geometry. So oftentimes, for most cases, the 3D Interconnect is definitely the way to go. A lot faster, better geometry. Got the link back to our native geometry. So you'll get a lot of times cleaner translations and faster translations. So wrapping up with 3D Interconnect, really know that it's an intuitive multi-CAD design platform. It's bigger than just translation. It can be used for references that need updating and oftentimes provides cleaner translations. So a lot of times we'll get the question of what now? What can we do now? First and foremost, give a shot at running import diagnostics. You might find in an area where you have problems that might be caused from bad, faulty geometry. Attempt some dumb solid manipulation. Try using delete and move face. You might just like it. Then attempt a FeatureWorks recognition. So try and go through editing maybe a imported part. And turn on and use 3D Interconnect for your workflows.
Again, another shout out to Brandon. Thank you so much for putting this together. Appreciate everybody for joining us. Stay safe, and hopefully we'll see you in a future webcast. Everybody have a great rest of your day.